Hey, I'm back. All right, so I think I got my computer figured out. Um, but I've said that before, and I was wrong. So we'll see how it goes. We see how it goes. So what I want to get into now is talk about these two flavors, reductionism and eliminativism. And to understand what that's about, it really helps to get into some philosophy of science. Philosophy of science is a topic unto itself, and I teach a course called Philosophy of Science, and we're gonna have to get into a little bit of philosophy of science to make further progress on understanding neurophilosophy. But you know what? Let's do it. We can do it. It's not that hard. So, philosophy of science is interested in what one thing it's interested in is the relationship between different theories. One thing that happens in the history of science is you've got one theory, and then later on you get another theory. And here's a question: What happened? What happened there? You might say that within a given domain, like in physics, you've got one theory, and then it gets replaced by another theory. And you might wonder, like, are there any interesting relationships between those two theories? So, for example, Newtonian mechanics gets replaced by Einsteinian mechanics. Newton had a certain scientific way of understanding the way objects move through space, laws governing the accelerations of objects and gravitational attraction between the objects. And then Einstein came along, and he also had a theory, and he also talked about objects moving, and they had mass, and there was gravitational attraction. So there's certain overlap. There's certain interesting, looks like commonality between the theories. But also, you might think that the Einsteinian theory replaced the Newtonian theory, and so what got thrown out and what got retained are two questions that are really important in understanding theory replacement. So, one way of thinking about reductionism and eliminativism in connection with neurophilosophy is they're two different sorts of relation that obtain between theories. So, one sort of thing that happens when a scientific theory replaces another scientific theory is there's some reduction going on. And another sort of thing that happens when one scientific theory replaces another scientific theory is that there's some elimination. So, in the one case, you got things being reduced, and in the other case, you got things being eliminated. And that's what we need to understand is what is the difference between a reduction and elimination. So, again, let's look at examples from the history of science that aren't examples concerning the mind, and we're going to use this to build up some analogies to talk about the mind. So bear with me. Let's talk about some stuff that probably is not the mind. So let's talk about, for example, I don't know, heat. So there's a thing that people were curious about, heat. And if you want to study heat, there's certain things you got to know about heat. You got to know that objects can be heated. You can change the temperature of objects. I mean, did you know that you can change the temperature of objects? And so you could have a piece of metal, and the metal could be very hot, or you could have a cold piece of metal, and don't drop it in your lap. That might be unpleasant. Another thing you might notice about objects that have different temperatures is that the temperatures can change. You can start off with a cold object, and it could get hot. And by the way, what I'm saying about objects also applies to quantities of like substances. So you can have some coffee, and the coffee got cold. I'm gonna drink it anyway, but it got cold. So there's the liquid, and there's the air I'm breathing, and that has a temperature also. And anyways, you might say that like you take some hot coffee and you put it in the coffee cup. Coffee cup is initially cold. Coffee is hot, and then the coffee cup, the mug itself, its temperature goes up, and then the temperature of the coffee goes down. So these are some facts that you can observe about heat and the way heat behaves and the way heated objects or heated substances influence each other. So now here's an old theory. This is a theory that eventually got replaced. And it's a theory that says what heat is, it's a substance unto itself. So when the coffee is hot, it has a lot of heat in it, and the heat is a thing separate from the coffee. It's in the coffee, but it's not itself the coffee. The heat is like this really fine substance that scientists used to call caloric. And if the word caloric reminds you of the word calorie, there's a good reason for that, and I'm not going to tell you what it is. You gotta go look it up. We don't have time for that connection between caloric and calorie, but that's the similar sort of word. But anyways, this old idea was that there was this substance they called caloric, and if you had a hot piece of metal, and you had a piece of metal that had a lot of caloric in it. It was just filled up with caloric, dude. And then you put an ice cube on the hot piece of metal, or you put a cold piece of metal on top of the hot piece of metal. And what's going to happen is that all the caloric that's like built up inside the hot piece of metal, it's going to flow into the cold piece of metal. And then eventually you'll achieve some kind of equilibrium where a certain amount of caloric has flowed out of the previously hot piece of metal into the cold piece of metal until they're about equal. Just like if you had a lot of gas in one container and then another container that was just vacuum, there's no gas in it, and then we connected them and we opened up some valve, the gas pressure from the one container, I lost track of the containers. The gas is going to flow from the one container to the other until you get equilibrium. You get similar pressure between the two containers. This old theory of heat said that heat was a substance itself, caloric, and there could be various amounts of pressure that determine the flow of caloric. That's an old theory of heat. That theory got replaced by a new theory of heat. And this new theory of heat says that there's no such thing as caloric, that hot objects, hot coffee, hot air, it's not hot because it's got a bunch of caloric in it. The air, the coffee, the mug, they're all made out of molecules, and the molecules are moving. Sometimes the molecules are just wiggling. Sometimes the molecules are flying all over the place. And heat is this it's this energy. It's the energy connected with the motions of the molecules. It's the kinetic energy of the motions of the molecules. And you might say that temperature itself is the average kinetic energy of collection of molecules. And heat is the amount of I'm losing track of it here. It's how much energy there is. So the difference between heat, there's a slight difference between heat and temperature. We might think of so for example, suppose you had a big swimming pool that was you know, you wouldn't call the water hot. It might be a little cold. You might have take a long time walking into it because it's cold. But it's a big swimming pool. And then we've got a small, compared to the swimming pool, small cup of coffee. It's really hot. You don't even want to stick your finger in it. You got to blow on it to cool it down a bit. So the cup of coffee has a higher temperature than the water in the swimming pool. But the water in the swimming pool has more heat. It's a lower temperature, but it's got more heat. So because the swimming pool is so big, it's got more kinetic energy in all those molecules. But the average kinetic energy is lower. So anyway, that's the difference between heat and temperature. But notice this new theory, it doesn't, when it talks about heat and when it talks about temperature, it's not talking about this separate thing, which is caloric. There's just the molecules, and the molecules are moving around, and that's what's going on with heat. So in this case of theory replacement, we've got the old theory, the caloric theory of heat, and then this new theory that has to do with molecular motion. We've got a case of elimination. The theoretical concept of caloric gets eliminated. And one way of describing elimination is to say we no longer believe that caloric exists. We now say that caloric doesn't exist. So there's an example in which theory replacement goes along with elimination. But using the same general example, we can illustrate reduction. So we still believe in heat, we still believe in temperature. That's part of the old theory, and it's also part of the new theory. The new theory says that what temperature is the average kinetic energy of the molecule. So heat or temperature reduces to, it's identical to the average kinetic energy. So in terms of old theory and new theory, we've got this old part of the theory, the part of the theory that is the word heat, and the part of the theory that is the word temperature. Those words are retained. The new theory still uses those words, so those words are retained, and the new theory defines those old words in terms of these new concepts. The new concepts of molecules, the idea of molecule, that's kind of new. That was kind of a new thing. The idea of atoms, the idea that they're moving around, and it is defining heat in terms of these new concepts, and so heat is being reduced to the new concepts. So this is similar to saying that water is H2O. People believed in water for a long time. They said things like, hey, uh, dost thou want some water? Bringeth unto me some water. That was old-fashioned water talk. And then later on, we find out about things like hydrogen and oxygen, and we postulate that hydrogen and oxygen is made out of atoms. There's such a thing as the smallest piece of hydrogen and the smallest piece of oxygen, and we postulate or discover that water is made of molecules, and the molecules are H2O molecules. The molecules are assembled out of hydrogen atoms and oxygen atoms. So we still talk about water, but we now say that what water is identical to is H2O. So water has been reduced to H2O. But other examples in the sciences where there's a new theory that replaces an old theory, we don't retain everything that's in the old theory. We say that we should eliminate those parts of the old theory, and we should say that what the old theory thought it was talking about ultimately it doesn't exist. So other sorts of examples from the history of the sciences of elimination would include the elimination of the luminiferous ether. Students that were in my space-time class last semester are familiar with this idea that so-called empty space is actually filled with a really fine substance called the ether or the luminiferous ether, and the luminiferous ether is the medium through which light waves propagate. On this old theory, just like sound waves propagate through medium of air and water waves propagate through the medium of water, so must light waves propagate through a medium, and let's call that medium the luminiferous ether. And we don't have to get into it now, but like back last semester, we talked about the Michelson-Morley experiment and other sorts of reasons for believing there just was no such thing as a medium through which the light waves were propagated. So we've got another example of elimination. Just like caloric got eliminated, so does the luminiferous ether get eliminated. We just say, it doesn't exist. We used to think it existed, but we were wrong. We're sorry. Please forgive us. Now, what's another example of elimination? Here's one from biology. I like this one a lot. There's this old theory in the biological sciences, the sciences of life, that said that what distinguishes living matter from non-living matter is the presence of a special substance known as the elan vital, the life essence. And so, if you've got just like a lump of coal, it's got no elan vital in it. And that's why the lump of coal just sits there, and you try to talk to it, it doesn't talk back. It's no fun. And you try to scare it, you're like, boo, or you insult it, like, go to hell, piece of coal. It doesn't care. But if you had like a living thing, and you thwack it, or you pour some salt on it, it might say, "Ouch! Please stop doing that," or it might just shrivel up and weep. Why? Why? Why do living things grow and reproduce? Well, because they've got elan vital in them. They've got the special magical what's it juice. And now we don't believe in that anymore. In biology, we think that the functions of that living organisms perform can ultimately be explained in terms of the activity of chemicals. So reproduction is ultimately something that can be explained in terms of chemicals like DNA. DNA is a deoxyribonucleic acid, something like that. That's a chemical. It's a really long, complicated chemical chain where you've got these different pieces, and they are encoding information, which is genetic information. And if you're going to make babies, here's how you do it. You got to take some DNA and like split it up and make copies of the DNA. And the DNA is ultimately kind of a chemical blueprint that allows for the production of proteins and other sorts of things inside of cells, and governs the growth of cells, and governs the activity of things like mitosis, the splitting of cells that's important for reproduction. So when you think about how life works, how a living organism works, ultimately it's explainable in terms of the way the chemical parts interact. There's no separate thing, which is the life force. Just like with the case of the hot cup of coffee, there's no separate thing in the coffee, which is the caloric. There's just the coffee molecules. And if they're moving around really fast, then that's hot coffee. And if they're moving around really slow, that's a coffee popsicle. And I'm sure it's delicious, a frozen chunk of coffee. But it's the story is not one about there being more or less caloric. There's just more or less motion in the molecules. And similarly, the difference between whether a dog is alive or dead, it has to do with how its molecules are moving around. If your molecules stop moving around in the right way, you're going to die. So take care of your molecules. Keep them, doing the right motions. I mean, it sounds simple. It's actually a little complicated, but there's no magical special juice, which is the elan vital. So there's another example of theory replacement accompanying elimination. So we've got caloric, that got eliminated. We say the caloric doesn't exist. We've got elan vital, that got eliminated. We say that doesn't exist. We've got luminiferous ether, that got eliminated. That doesn't exist. But in the case of heat, heat didn't get eliminated. Heat got reduced. So we keep on talking about heat. We have retained talk about heat, but we reduce it to average kinetic molecular kinetic energy. We keep talking about water, but we reduce it to H2O. We say that water exists, but what water really is a chemical combination of hydrogen and oxygen. Hey, babe. Yeah. I'm trying to make a video. Yeah. You want to come here and be in my video?